We continue our next discussion on matter, and we explored the molecular model for solids, liquids and gases. Now this model is based upon the motion of molecules. This model is purely based upon the motion of molecules, or you can say it is based upon the kinetic energy of the molecules, because the moving molecules will always possess some kinetic energy. So you can say that this model is also based upon the kinetic energy of the molecules. As we already know that molecules are in continuous random motion, and definitely during motion they possess kinetic energy. So this model is a comparative study of the behavior of the molecules of solids, liquids and gases. So if we consider a solid, according to this molecular model, the particles of the molecules of the solid are very closely packed or densely packed molecules. They are quite close to each other, and so the intermolecular force is the strongest. Intermolecular force is the strongest among the three states of matter, that is solid, liquid and gases. Now the molecules of a solid, as they are closely or densely packed, they vibrate about their mean position. They do not leave their most position. The molecules vibrate about their mean position and do not leave their place. So this describes the behavior of the molecules of a solid. If we are talking about liquids, then the liquid molecules are less densely packed. So if you compare solids, liquid and gases, you can say that the molecules are quite close, but they are less densely packed as compared to solids, or you can say the intermolecular space is not as small as compared to that of solids, but definitely it is greater than that of gases. So you can say that they are loosely packed. The molecules are loosely packed. Intermolecular force is not the weakest, but it is weak as compared to solids. Now these molecules of a liquid, they can leave their position, the molecules can leave their position and they can move on the boundary of the liquid. The molecules can leave their position and move within the boundary of the liquid. That means the molecules are capable of moving within the liquid and within the boundary that the liquid will occupy when it is placed in a container. So the molecules are quite capable of leaving their position, unlike the molecules of a solid, and they restrict themselves within the boundary of the liquid. And definitely, if you compare the intermolecular space is least, the intermolecular force is strongest in case of solid. As compared to solid, the intermolecular space is slightly more in liquids and the intermolecular force is weak as compared to solids. On the basis of this molecular model, we can realize that solids are more or less rigid. Solids are rigid, that means they have a definite shape. They have a definite shape and volume. Whereas liquids do not have a shape, but they have a volume. And they generally occupy the volume that they are capable of when they are kept in a container. So do not have a shape, but have a volume, a definite volume. Now, on the basis of this molecular model, if we try to explain the behavior of the molecules of a gas, then we realize that in the case of gases, it is least densely packed. The molecules are far apart from each other, and so they are least densely packed. They are quite far apart from each other. The intermolecular force between the gaseous molecules is the weakest among the comparison of solids, liquid and gases. Is weakest among all the three. And so the gaseous molecules are capable of vibrating about the mean position. Not only that, they can leave their position, they can move throughout the entire space available to them, and so they are in random motion. They move from here and here to there within the entire volume that they will get. They are random. They move haphazardly. And so, we do not have a shape, neither do we have a volume for a gaseous material. So, gases do not have a shape. They do not have a volume also. A definite volume. But definitely, if a gas is enclosed in a container, it will occupy the entire volume of the container. So we say that they do not have a definite volume. They will occupy the entire space that is available to them. So this is a comparative study of gases, solids and liquids on the basis of the molecular model. Now the discussion of the molecular model can be extended to the state transition that occurs when a solid gets converted to liquid or a liquid gets converted to gas and vice versa. So let us discuss about the change of state or state transition. Change of state or state transition, or sometimes it is also called as phase transition. So when a substance gets converted from solid to liquid or liquid to gas, it is called as state transition. So state transition or change of state, it is the phenomenon of change of state from one state to another. You can say it is the process of from one state to the other. The process of change from one state to the other by simply absorbing heat or liberating heat. absorption of heat or rejection of heat. So when a substance is in the solid state and it absorbs it, then it can go to the liquid state. Or a substance in liquid state, if it rejects it, it can go to the solid state. Now this happens at a constant temperature. The temperature does not vary whenever the substance is changing its state. So you can say that it is definitely a process whereby there is a change in state from one state to the another by absorption of heat or by rejection of heat. And that happens at constant temperature. The temperature does not vary during the process of state transition. So this situation can be easily narrated by a diagram. So suppose there exists a material in solid form. If it absorbs it, it will go to the liquid state after a sufficient amount of time and after absorbing a sufficient amount of heat. It is not that you provide some heat to a solid and it will immediately go to the liquid state. The solid will absorb a requisite amount of heat and at a particular temperature it will get converted into the liquid state. So you can say that solid to liquid will require absorption of heat absorption, and the process of conversion of solid to liquid is called as the process of melting. So in this case, some heat is absorbed and at a particular temperature the solid will get converted to the liquid state, and that temperature is called as the melting point of the solid. The opposite phenomenon can also happen. The substance in its liquid state can go on rejecting a considerable amount of heat, and after some time it gets converted to the solid state, and the process is called as freezing or fusion. And this process will involve some amount of heat rejection or liberation of heat. Now when a solid gets converted to a liquid at a specific temperature, that temperature is called as the melting point of the solid, and when a liquid gets converted to the solid form at a particular temperature, it is called as the freezing point of the liquid, and both the melting point and the freezing point are same. The melting point of a solid and the freezing point of a liquid is same. If we consider the example of ice versus water, so ice will get converted to water at 0 degree centigrade and water will freeze to ice at 0 degree centigrade. So we can say that the melting point of ice is 0 degree centigrade and the freezing point of water is also 0 degree centigrade. Similarly, if a liquid gets converted to gas, it will absorb some amount of heat. So heat is absorbed, and the process of conversion of liquid to gas is called as vaporization. And heat will be absorbed in this case. And when a gas gets converted to liquid, it will reject a requisite amount of heat, and the process of conversion of gas to liquid will be called as condensation. And definitely, when a gas condenses to liquid, it will reject some amount of heat. Again, the temperature at which a liquid gets converted to its corresponding gaseous form, that temperature is called as the boiling point of the liquid, and the temperature at which a gas will get converted to its corresponding liquid form will be called as the condensation point of the gas, and both are exactly identical. So the boiling point of a liquid is is same as the condensation point of the corresponding vapor form. For example, water absorbs some amount of heat and gets converted to gas at 100 degrees centigrade. Similarly, water vapors condense to water at 100 degrees centigrade. It is not necessary that every solid will get converted into liquid and then into gas. There are some examples where the solid directly gets converted to gas, and the process whereby a solid will absorb some amount of heat and get converted to gas is called as sublimation. A very good example of sublimation is camphor. Iodine crystals, they absorb heat and immediately they convert to their vapor form. So in the process of sublimation, heat is absorbed by the solid and the solid directly gets converted to the gaseous form or the vapor form. You can take examples like camphor, iodine crystals, etc. And the opposite phenomenon, that the conversion of gas to solid when the gas is cooled, that process is called as deposition. So gas to solid conversion without going into the intermediate liquid form is called as deposition. And in the process of deposition, the gas will reject some amount of heat. Same example you can take when the iodine vapors are cooled, they immediately get converted back into solid iodine, and further cooling will produce the crystal form of iodine. So this is an example of change of state, and we can explain this change of state on the basis of the molecular model also. Remember that whenever state transition or change of state occurs, that occurs at a constant temperature, whether it is solid to liquid, liquid to gas, or any other form, it happens at a constant temperature. The heat absorbed or heat rejected in any of the processes that I have mentioned, there is no increase or no decrease of temperature. You can note it down. Now, on the basis of molecular model, we can also explain this phenomenon and why the temperature remains constant. Before discussing the molecular model, some points are noteworthy. The melting point, the boiling point, etc. is easily altered by changes in pressure and by adding some impurities. For example, you can say that water expands on freezing, whereas other substances like wax, lead, etc., they contract on freezing. Now, when we are talking about wax and lead, we are considering the molten form of wax and lead, so that will contract on freezing, whereas water will expand on freezing. Now, it happens, this behavior of water is called as anomalous behavior of water because it is not behaving like other substances, other common substances. If you look at the density versus temperature graph of water, then you will note that the density of water is maximum at 4 degrees centigrade. The graph is of this form, more or less. So at 4 degrees centigrade, the density is maximum. Suppose this is 0 degrees centigrade. So when the temperature of water is decreased from 4 degrees centigrade to 0 degrees centigrade, the temperature of water is decreased, then you see that the density is decreases. You know that density is mass by volume. So if density is decreasing, it means that the volume has increased, because for a given mass the density is inversely proportional to volume. So if the volume increases, then only the density can decrease. So when water is cooled from 4 degrees centigrade to 0 degrees centigrade, that means when you are approaching the freezing point, definitely the density is decreasing, which means the volume is increasing, and that's why we say that water expands on freezing. But this behavior is totally different from common substances like wax and lead. In the molten form, they will contract on freezing, and will definitely expand on cooling. So this is a behavior which is called as the anomalous expansion of water. If we increase the pressure, then the melting point of ice will decrease. Decreases on increase in pressure. So melting point of ice decreases on increase in pressure, whereas melting point of wax and substances like wax decrease on increasing pressure. If we add impurities to ice, its melting point will also decrease. Melting point of ice will also decrease. Decreases on addition of impurities. Say for example, if we add salt to ice, its melting point decreases, and it can decrease up to minus 18 to minus 20 degrees centigrade. The actual melting point of ice is 0 degrees centigrade, but on addition of impurities such as salt, addition of salt to ice will roughly decrease the melting point to around 18 degrees centigrade to some minus 22 degrees centigrade, minus 18 to minus 22 degrees centigrade. It depends upon the amount of impurity that we have added. And this is also called as freezing mixture. The mixture of salt and ice is also sometimes called as freezing mixture. Whereas if you talk about the boiling point, both on increase in pressure and addition of impurities, the boiling point of water definitely increases. Boiling point of water increases with increase in pressure. And that is why it becomes easy to cook in a pressure cooker. The example of pressure cooker where deliberately the boiling point of water is made to increase, so the food gets considerable time to get cooked. Is the best example where we alter the pressure or increase the pressure and thereby the boiling point increases. At high altitude, the atmospheric pressure decreases And that's why water takes more time to boil. It takes less time to boil and the food gets unprepared. At high altitude, the boiling point of water might decrease up to 80 degrees centigrade, whereas the actual boiling point at sea level is around 100 degrees centigrade. But with increase in pressure, you can enhance the boiling point of water to around 120 degree centigrade. That happens in a pressure cooker. Addition of impurities also will increase the boiling point of water. If we add salt to water, its boiling point will increase. With addition of impurities. So these are some important points regarding the melting and boiling point of water. Now we look forward to the molecular model and the explanation of change of state on the basis of the molecular model. So suppose we consider the case of solid to liquid transition. What happens when a solid gets converted to liquid? It will definitely absorb some amount of heat. Now, whenever the solid will absorb heat, its molecules will gain kinetic energy. They will leave their position and they will vibrate more vigorously. And when they vibrate more vigorously, then the intermolecular force decreases, and after some time the solid has accepted sufficient amount of heat and the molecules have gained sufficient amount of kinetic energy and they get converted to the liquid state, and that happens at constant temperature. So you have to remember this. I repeat, whenever a solid absorbs some amount of heat, its molecule, the heat is absorbed by the solid, the molecules gain kinetic energy. And when they gain kinetic energy, they vibrate more vigorously. And when they vibrate more vigorously, the intermolecular force decreases. The intermolecular force begins to decrease. This process will continue as long as the substance in its solid form is absorbing heat. The molecules continuously gain kinetic energy, they vibrate more vigorously, the intermolecular force decreases. A time comes when the solid has gained sufficient amount of heat so that the intermolecular force is now small sufficiently, and the solid is at the verge of getting converted to its liquid form. And that conversion will occur at a constant temperature that is called as the boiling point. The melting point of the solid. This melting point will be a constant temperature for a particular solid, and when the solid begins to get converted to the liquid form, the process of heat absorption continues, but now the molecules that have gained kinetic energy start vibrating more vigorously or more violently. And after gaining sufficient amount of heat energy, a time comes when the molecules will overcome the intermolecular force. So when these molecules gain kinetic energy and have already overcome the intermolecular force, they are now free to move, and thereby the solid gets converted to the liquid form. So until the melting point has reached, the molecules are gaining kinetic energy and they are vibrating more vigorously and more violently, and after gaining sufficient amount of kinetic energy, when the melting point has approached, the solid molecules now overcome the intermolecular force, they get widely separated and ultimately they get converted to the liquid form. And at the melting point, the heat absorbed now becomes constant. The heat absorbed is not really constant, it is the melting point which is constant, and so the heat absorbed now does not change the kinetic energy of the molecules. The heat absorbed when the solid is slowly getting converted to the liquid form, the heat absorbed only increases the potential energy of the molecules. And this potential energy is the energy that the molecules will possess due to the separation that they will maintain in the liquid state. So the heat absorbed now will only increase the potential energy of the molecules, but kinetic energy of the molecules will not change. And as kinetic energy does not change, the temperature remains constant at the melting point. So until the entire solid gets converted to the liquid, the heat absorbed will only increase the potential energy. And therefore the heat absorbed will be utilized to do work against the intermolecular force, which will increase the intermolecular separation. So this heat absorbed is utilized to overcome the force of attraction between the molecules. And this will definitely increase the potential energy of the molecules. The kinetic energy does not change. Because kinetic energy does not change, the temperature remains constant at the melting point. So there is two stages of realization of this situation. Initially, the molecules are gaining kinetic energy, the temperature is increasing, the intermolecular force is beginning to decrease, the molecules are vibrating more vigorously, but when the solid reaches its melting point, the temperature remains constant at the melting point. From there on, the heat absorbed only increases the potential energy of the molecules, and the molecules are now more free to move and they convert to the liquid state. And so the heat absorbed will only be utilized to overcome the force of attraction between the molecules. This heat absorbed is also called as latent heat. This heat absorbed during the transition from the solid to the liquid at the melting point, this heat is called as the latent heat. Latent means hidden. So the heat does not show its presence by increasing the temperature. The heat is completely utilized to overcome the force of attraction only. It does not bring about any increase of temperature. It does not increase the kinetic energy of the molecules. That's why this heat is also called as latent heat. So from solid to liquid transition, this latent heat might be called as latent heat of melting. From liquid to solid conversion, the latent heat might be called as latent heat of fusion. It might have different names, but the relation of latent heat is that the latent heat does not bring about any change of temperature. It is purely utilized to overcome the force of attraction and increase the potential energy due to molecular separation. Now, the same theory also applies when a liquid gets converted to the corresponding gaseous form. So whenever a liquid is heated, initially its temperature will rise. So liquid to gas conversion or liquid to gas phase transition, and heat is absorbed, and ultimately the temperature becomes constant when the process of conversion is going on. Temperature becomes constant at the boiling point. So the same approach here also occurs. Initially, the liquid is absorbing heat. The heat that is absorbed by the molecules will increase the kinetic energy of the molecules. So when the kinetic energy of the molecules goes on increasing, the molecules are now more free to move. In liquid state, the kinetic energy of the molecules is definitely greater than the kinetic energy of the molecules in the solid state. But still, whenever the molecules were in the liquid state, they were free to move within the boundary of the liquid. And what happens is that when they go on absorbing heat, they more vigorously or more violently move and they gain sufficient amount of kinetic energy. So this process continues until the boiling point is achieved. Whenever the liquid achieves its boiling point, the temperature becomes constant. The temperature remains constant. The heat energy that is absorbed when the liquid is at the verge of getting converted to its corresponding gaseous form, the heat absorbed is now utilized to increase the potential energy due to molecular separation, and whenever the potential energy increases, the heat absorbed is utilized to do work against the force of attraction between the molecules. And as the force of attraction is overcome, the molecules are now more free to move and they try to occupy the entire space available to them. The molecules now leave the surface of the liquid and go into the corresponding vapor state. So this heat absorbed thereon increases the potential energy. The kinetic energy is no more changing, the temperature remains constant. That we have already discussed in the solid to liquid conversion. The same situation is also happening here, and the heat absorbed is utilized to do work against the force of attraction that exists between the molecules. And now the liquid molecules, they leave the surface of the liquid and go to the vapor state. Go to the corresponding vapor state or gaseous state. Again, the heat absorbed in this situation, when the temperature becomes constant at the boiling point, this heat is also called as latent heat. It can be called as latent heat of vaporization because we are studying liquid to gas transition. So this latent heat can be called as latent heat of vaporization. Obviously, in the opposite process, that is gas to liquid conversion, it can be called as latent heat of vaporization. Instead of latent heat of evaporation, we will call it latent heat of condensation from gas to liquid conversion. So the same molecular model, the same approach of the molecular model can be realized in any type of state condition. Now if the opposite would have happened, from gas to liquid or from liquid to solid conversion, the heat will be continuously released by the material or by the particular substance, and then if the heat is released, definitely the kinetic energy will go on decreasing, the temperature will also go on decreasing, and until the temperature reaches the freezing point or the temperature reaches the condensation point, the kinetic energy decreases and the temperature decreases. But as the melting point, the freezing point or the condensation point is achieved, the molecule do not change their kinetic energy, because the heat now that is released is just trying to bring about the state transition, and so the temperature becomes constant, and again it can be called as the latent heat, or the latent heat of condensation, or the latent heat of fusion. So in both the situations, liquid to gas or solid to liquid, or the opposite situation, at initial phase the kinetic energy increases or decreases and the temperature increases or decreases. But when the phase transition or the state transition begins, the temperature remains constant and the kinetic energy does not change. The potential energy of the intermolecular separation goes on increasing or decreasing, and thereby the heat now is called latent heat.